So, yes, I want to talk to you guys about quaternions. And do anybody know what they are? Do you have any sense of it? Have you ever heard of them before? Anybody ever heard of a quaternion before? No? How many of you heard of vectors? Okay, good. I've talked about those all semester. I hope you heard about those. Well, before there were vectors, there were quaternions. Quaternions used to sort of play the role that vectors do now in terms of being an object which we use to formulate statements about three-dimensional coordinate geometry, right? I think to properly understand quaternions, it might be wise to just spend a second to talk about complex numbers. All right. So, complex numbers also have, a geometric origin, let's say. So let's just talk about complex numbers for a second here. So x plus iy, right? You guys know complex numbers. No, but have you guys ever, I don't think I've talked about it in here, but every complex number can be put in what's called polar form. Do you guys know about the polar form of a complex number? Well, you guys know polar coordinates, right? So if I was to graph x plus iy, like here, that means that this is y, right? And this is x. And so if I go like that, make this angle theta, call that distance r, you guys know the deal. Y is equal to r sine theta, and x is equal to r cosine theta, right? And so if I have z is x plus iy, I can write that as r cosine theta plus I times r sine theta, right? Where r is what? Square root of x squared plus y squared, right? All right, so you can factor the r out, and that will give you cosine theta plus I times the sine of theta, right? And a notation people used to use for this would be this, RCIS theta. But I don't like this cis notation. So I say no to this, none of that. I like normal notation. So z equals to r e to the I theta is the way I prefer. So this is the polar form of complex number, right? And here I'm introducing the imaginary exponential. E to the I theta is by definition cosine theta plus I sine theta. Okay? Now, what happens if you have two complex numbers, right? How do we multiply complex numbers? Suppose I have, z is x plus iy and w is a plus ib, right? Z times w is what? We got what? xa minus yb plus I times xb plus y. I mean, however you want to write it. Agree? Disagree? What do you guys think? Can you tell me what that means? What is z and what is z times w as it relates to z and w? Geometrically, can you tell me? Anybody know? I mean, I think if you look at this formula, it's pretty hard to say. Okay? I don't think it's at all obvious, actually. But look what happens if we use polar form. So we write z equals to r e to the I theta. And we write w is equal to, let's say, s e to the I beta. Right? And what happens when I calculate z times w? I have r e to the I theta times s e to the I beta. Right? And so r and s are just real numbers, right? They're the length of z and w respective, right? How do you think it works if we do e to the I theta times e to the I beta? What is that? E to the I what? Care to guess? Very good. It is e to the I theta plus beta. So let me ask the question again. Geometrically, what's the relation of zw to z and w? Like, what is this geometrically? Let me write it out. I mean, this is, so apparently, the length of zw is equal to rs, which is, by the way, the product of z times the, so it's the, this is the length. The length of zw is the product of the lengths of z and w. You multiply two complex numbers, how long is the resulting number? The product of the numbers you multiplied. Right? And how about, what was this theta plus beta? And the angle of z times w apparently is equal to the angle of z plus the angle of w. Right? If you'll allow me the notation, angle of like r e to the I theta, let's say that angle is theta, right? I'm glossing over some ambiguities here because the angle is not defined uniquely. We always have the 2 pi degeneracy of the angle, right? We could use 0, or we could use 2 pi, we could use 4 pi, we could use 6 pi. These geometrically are all the same angle. Yeah. So, example, if I have z is r e to the I theta, and I do z times e to the I beta, what's that give me? What's going on here? What's it doing? What is the effect of multiplying by e to the I beta? Adding beta to the angle, right? So it's like it's over here or whatever, right? So beta right, which is, well, anyway, you got the idea. So, can you put that into words? What is that? What's going on here? Multiplying by the imaginary exponential e to the I beta rotates the point, angle beta. It's a rotation in the two-dimensional sense, right? And what happens, like, a less interesting example, but what happens when I do like a constant times x plus iy? What's that do? That's just rescaling the point, right? So if you look at this all together, multiplying complex numbers is simultaneously folding in the ideas of rescaling a two-dimensional vector and also rotating a two-dimensional vector. Right? And it does this, rotations and dilations in 2 dimensions, in such a way that the complex number system forms this beautiful, complete algebraic system, right? You know what I'm talking about? Complex number algebra. The thing I haven't talked about yet today with complex numbers is we can talk about z conjugate, right? Which is, 5x plus iy. How's that go? X minus iy, right? The complex conjugate. What does complex conjugation have to do with length or anything? Have I talked about this before in here? I don't think I have. We should talk about this in every math class that we teach, because it's not done justice to in high school. It just isn't, and it's important for everybody to know about this. Because complex numbers are not something esoteric or imaginary. They're actually just as real numbers, and they're actually extremely insightful. So anyway, here z times z conjugate, what happens? We get x squared, minus ixy plus ixy minus I squared y squared, right? Also known as what? So there's actually a formula. The length of z is the square root of z bar. So something you probably learned in high school, and maybe, I think you probably even used it in this course at some point. How about, when is a complex number invertible? When does it have a multiplicative inverse? We want what? 1 over z, whatever that means, times z should be equal to 1, right? When is that actually going to be plausible? It turns out any non-zero complex number has a multiplicative inverse. That's part of what makes complex numbers so very special. And the formula for those, if I have 1 over x plus 1 over x, 1 over x plus iy, what's the formula for the inverse? How do you actually put this into practice? You multiply by the complex conjugate, right? X minus iy over x plus iy times x minus iy, which gives us what? X minus iy divided by x squared plus y squared, right? In the complex notation, that's 1 over z is just equal to z bar over z bar. That's a formula for calculating the inverse to a complex number. Geometrically, how is the inverse of a complex number related to the complex number? Let me ask that question. Z is equal to 2 e to the I pi over 4. Geometrically, analyze Z inverse. Right? So 1 over Z, 1 over 2 e to the I pi over 4 is equal to actually 1/2 e to the minus I pi over 4. So if I graph these, what happens, right, is the number originally is distance 2 from the origin, right? Here's the unit circle. So the number here is distance 2 from the origin, and reciprocating the number, the complex number, has the net effect of moving it distance 1/2 from the origin and down here, right? Here's z inverse. So reciprocation is actually really interesting for the complex plane if you think about it. What the reciprocal function does for the complex plane is it takes all of the points outside the unit circle and it does what? It flips them inside the unit circle. And it takes all the points inside the unit circle and it flips them outside the unit circle. Like the process of inverting a complex number, if you think about it, what it does to the complex planes, it like literally turns it inside out in some sense. But it also does what? It leaves the unit circle in place, but it rotates it. It moves theta to minus theta. So this is the start of a much longer discussion, like how do you understand graphing complex functions? You know? That's what we look at in Math 331 in part, the complex analysis course. All right, so there's a taste. I hope I've convinced you that complex numbers are intricately tied to two-dimensional coordinate geometry, right? Agree? Any question of two-dimensional coordinate geometry, you can reformulate it in terms of complex notation and see things that would have been very difficult to understand in real notation. Using complex notation for two-dimensional problems is a game changer if you're really good at it. So it was in light of this that Hamilton started trying to do the same thing for 3 dimensions. Right? If complex numbers are so useful for understanding rotations in 2 dimensions, there's got to be some kind of system of numbers, right? Some sort of multiplication of 3-dimensional vectors that will do the same thing for rotations in 3 dimensions, right? Seems reasonable. 10 years later, he decided no. So like Hamilton spent 10 years trying to find a multiplication on 3-dimensional space which was analogous to the algebra that we know and love from complex numbers. Couldn't be done. And you can prove that. I mean, I would have to make more formal the claim, like I would have to formalize what it is that Hamilton was looking for in order to prove such a claim, and that of course would be wholly inappropriate for this class, as this is not a proofs class. But what happened, as the story goes, is all of a sudden Hamilton realized in about 1843 or so that if he instead thought about 3 dimensions inside of 4 dimensions, if he added dimension, and think about the 4th dimension perhaps as time, in light of that construction, there's a way of doing a 4-dimensional multiplication, which actually can encode 3-dimensional rotations inside that larger context. Now, I'm not going to explain to you how that happens because it's ugly. And if you print out everything that there is on Wikipedia about quaternions, it's something like 70 pages. I know there's tons that's known about this, all right? But quaternions, which I'll use the notation H for, are things of the form T plus, let's say, xi plus yj plus zk, such that t, x, y, and z are real numbers, and I squared equals to j squared equals to k squared equals to minus 1. So quaternions are kind of like complex numbers because they've got these, they're called versors or imaginary units, I, j, k. Now I, j, k are not the same thing. They're linearly independent. You guys know what that means. But there's more. There's more. You see I, j, and k satisfy certain multiplication rules. I times j is equal to k. J times k is equal to I. K times I is equal to j. And by the way, j times I is minus k, and k times j is minus I, and I times k is equal to minus j. These multiplication rules define, paired together with, of course, the I squared equals j squared equals k squared equals minus 1, these define a multiplication of quaternions. Does that look familiar? That's the cross product, isn't it? It's like the cross product. This is actually why we use the notation I, j, k for cross products. It's actually an homage, it's in honor of Hamilton's quaternions. Because our vector formalism replaced the quaternionic formalism about 1900 or so, through the work of Oliver Heaviside and I think Gibbs. I'd like to know more about that history. I don't know enough yet. But anyway, so let me actually work out the multiplication of the quaternions. So if I call this thing, let's say, eta, I can write eta as equal to, let's say, t plus, if you'll allow me this notation, I'm not sure what the right notation is. Let me call it, I guess I'll just use this, if this is okay with, man, I don't like that notation. Let me just call it r vector. So here I mean r vector is xi plus yj plus zk for the current consideration. And I also want to look at yet another quaternion. Let's call it like alpha equal to, let's say, s plus, golly, I need another vector. For lack of imagination, let me call it like a, where a vector is like ai plus bj, but hopefully no danger of confusion there, right? Big A versus, okay, fine, there's some danger for confusion. Let me make that a v instead. There we go, now there's no danger for confusion. All right, so I got an r vector, I got a v vector. I want to multiply these two things and see what happens, okay? I think I got enough time, we're gonna make it. So what happens with eta times alpha? So I've got like t plus r vector times s plus v vector. And the way this works is you got like ts plus, t times v plus, s times r, and then plus r times v. All right, that's what the quaternion multiplication looks like. So a few different things going on here, right? We can kind of recognize what this is. This is just like scalar multiplication, right? That's like scalar multiplication of vectors. That's what that is. This over here, that's just old garden variety multiplication of real numbers, right? But this over here, this warrants further study, right? That's where the interesting stuff is going to happen. Let's look at that more detailed over here. It should go without saying that in the future lectures when I have some cool stuff I plan to talk about in time remaining, if on a particular day you have been studying, preparing for the final, and you have further questions about material we've already covered, it is totally within your right to raise a question and ask me, would you work out another example of such and so forth? Could you explain the general theory of that? I'm still a bit lost. Totally fine. I will answer those questions. I welcome them, but you have to ask them. I'm not going to ask them for you. Otherwise, I will cover interesting things. I'm still going to cover the interesting things, but just less of them if you ask questions. Okay, so RV, in other words, xi plus yj plus zk times ai plus bj plus ck. The way this quaternion multiplication works, guys, is just like normal, just like complex number multiplication works, right? The usual distribution laws, and what's the fly in the ointment, so to speak? Like, what's the difference? Well, the difference with the complex numbers is simply that I squared is minus 1, right? The difference with quaternionic multiplication is that we have an I, a j, and a k, and they have to multiply according to their rules that Mr. Hamilton there made up, you know? Story goes that he was in like a bathtub or something, and he had this epiphany, and he was like, Eureka, I found it, and then he went running around naked in the streets or something. I don't know if this is actually true or not, but I've heard this story for a while. If it's true, it's amazing. But, okay, so like you've got, I'll just write it out, okay? xa I squared plus yb j squared plus zc k squared plus xb ij plus ya ji plus zb I gotta pick a path here. Xz, no, not xz, xc ik plus c za, yeah, za ki oh, I've lost my way. YC JK plus ZB KJ. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I didn't miss anything. You guys with me? What happens with the first three terms? Oh, I better pick up the pace here. So this is minus xa minus yb minus zc, and then over here we've got, xb minus yak plus za minus xcj plus yc minus zbi, which in our usual notation is what? Minus r dot v plus, what's that? Well, you might not recognize it right offhand, but this is the cross product. So what this is the cross product. This is R cross V. So the quaternionic multiplication simultaneously encodes dot product and cross product. So if I go back over to here, RV was actually what? Minus R dot V plus R cross V. And there's like the general quaternionic multiplication. Now, if we look at, for example, eta times eta conjugate, what would that be? What should the quaternionic conjugate of a quaternion be, do you think? What are you going to do? I heard a t minus r. We have a winner. That's exactly what you do. And what happens when you multiply those out? So we get ourselves t squared, right? Plus tr minus tr minus rr which is what? T squared minus a minus r dot r plus r cross r. What's r cross r? No. What is the vector cross itself? 0. 0, right? And so what do we got here? T squared plus r dot r. And I think that was what you were just telling me. X squared plus y squared plus z squared, right? So this shows you that the length of a quaternion is the square root of the quaternion times its conjugate. And you can also then, of course, define 1 over a quaternion to be equal to the conjugate quaternion divided by quaternion times quaternion conjugate. There is an inverse to every quaternion, multiplicatively speaking, provided that the quaternion is non-zero. This is very special in the world of algebras. Like, I've studied algebras a lot. There's only a few that have this property. This is meaning it's almost a field. Every non-zero thing has an inverse. What makes this not a field, what makes this what's called a skew field, is that the multiplication is not commutative. It's sometimes anti-commutative. But this is as near as you can be to being a field and not be a field. It's a very precious and special example. But anyway, that's what a quaternion is. And you can use these to implement three-dimensional rotations. And there's like gaming software and stuff that's built over that mathematics. It's actually better than rotation matrices for certain coding reasons that I do not begin to understand, so please don't ask me.